Okay. Thank you, Bartek, for such a lovely introduction. I think that's one of the nicest introductions I ever received. And I must admit that if I knew that you prefer such that, then I actually would have prepared some pictures of my group in Brno together with Don Knut when he visited. Today, what I wish to talk about the uniform Turán density of hypergraphs, which is a topic that I have been working on mostly during last, let's say, 1.5 years. And clearly, when you look at the list of collaborators, you can see a significant COVID influence because most of them happen to be based in Brno, and there are only very few not based in Brno. And I will be mentioning, so the talk is not based on a single paper, there are several papers, so two main results that I wish to mention, and I will be giving the credit to particular co-authors when I will come to those results. I also trying to do kind of a hybrid, not only hybrid talk in the sense of hybrid in the sense that there's actually a good number of remote participants and as well as local participants physically present here, but also hybrid in use of technology. So I would normally perhaps present this topic on a blackboard. However, I think the blackboard would be challenging for remote participants. So I'm going with the tablet. And even if I prepare some slides, I prepare slides only mostly for some more complex pictures and so on. And as usual, like if you have any questions, please feel free to interrupt me and ask the question, like either like here physically, if the microphone will not capture the question, I will repeat it on the mic. And I also have a chat open on my screen, so I should be able to see any questions that can appear in the chat. Okay. So what I want to, so let me maybe start with some more general introduction, and I want to first start talking about Turán problems. So the talk will be about uniform Turán problems, which is a variant of Turán problem studied more recently. But I want to talk about, first give a historic overview. So I want to talk about Turán problems. And now let me double check that things can be seen. They can be seen. And I would like to mention some very classical results in this setting. And namely, I would like to mention the theorem of Mantel, which is perhaps one of the oldest theorem in graph theory. I wouldn't say the oldest one, it's actually some older one. And this theorem talks about the maximum number of edges that a graph without K3 can have. So, and I think I should slightly improve my font, but it's a little bit more legible. So in general, Turán problems ask how many edges can be in an F3 graph, where F is some specific graph, or one can even more generally consider a family of graph, and Mantel's theorem provides an answer to one of the simplest settings, namely the setting when we look at the triangle. And the answer is that the number of edges is maximized by the complete bipartite graph with parts of equal sizes. So let's say K and N. Maybe I can briefly sketch here how the graph looks. And during this talk, I will be working mostly in the asymptotic setting. So what I wish to do is I wish to be rather looking at the density of the edges. So in other words, the theorem says that the density of any triangle-free graph is at most 1/2. So one can define the density of a graph as the probability that if I randomly pick a pair of vertices, they will be joined by an edge. And Mantel's theorem, and I should have also put here the year, which is 1907, says that if I have a triangle-free graph, a graph that does not contain a triple of vertices joined by edges, when the density is 1/2. And similarly, another very classical result is the Turán theorem, which generalizes Mantel's theorem from the case of triangle to the case of general complete graphs. So let's say Kp. And again, we know here the answer precisely. And so let's say that if P is, let's say 5, then the best what we can do is we can split the vertices into 4 parts of equal sizes and put all edges between them. And so the density of Kp free graph will be at most P minus 2 divided by P minus 1. And as I said, we know the answer precisely, but if I'm just looking at the limit for the number of vertices going to infinity, then this will be the ratio. And these results were generalized to the case of general graphs by R dash, Stone, and Shimonovich. And the year I have in my notes is 1946. And the answer in general, if I'm looking at the density of H free graph, when the density is always at most the chromatic number of H minus 2 divided by the chromatic number of H minus 1. And this is tied similarly as in the previous cases. And here I really need the asymptotic version because the exact results, like unlike the previous results, which are really known, like the exact values here, like the value is known asymptotically. So this was a quick overview of some very classical results in extremal graph theory, but this talk should be about the hypergraph Turán problems, hypergraph Turán problems in particular with the uniform Turán density. But let me maybe mention how the situation look in the setting with the Turán problems in the setting of hypergraphs. And while we basically know close to everything in the setting of graphs, we don't know too much in the setting of hypergraphs. So in particular, if we ask in the setting of hypergraph, what is the maximum number of edges in a hypergraph, and let's say I will be looking at in the free uniform case. So in a free uniform hypergraph, meaning a hypergraph where every edge has exactly 3 vertices, in a free uniform hypergraph, avoiding the tetrahedra, alias K for free, when we don't know the answer. So it's conjectured. So there's a conjecture where the answer should be 5/9, and I will show the conjectured extremal construction. But the problem is open, and actually there's a monetary prize that R dash actually offered $500 for solving this problem. And if you manage to determine the optimal number for all complete free uniform graphs, and actually the price would be even $1,000. So let me show you the extremal construction, which will actually motivate the type of problems that I wish to be looking at today. So the extremal construction, or the conjectured extremal construction, looks that we split the vertices of our hypergraph into 3 sets of equal sizes. And now I should say where the edges are. So there are 2 types of edges. So there are edges that do contain one vertex from each of the parts. And when there are edges, so let's say I think of these parts as cyclically ordered, and when there will be edges that contain two vertices from one part and one vertex from the other. So there will be an edge like this, there will be an edge like this, and there will be an edge like this. And I do this for all the triples of vertices of this type. So it can be verified that the density of this free uniform hypergraph is 5/9, meaning if I randomly pick a triple, I will see an edge with probability 5/9. And this hypergraph does not contain K43. So maybe I should have also included here a picture of K43. So that's a graph that contains all triples. And now I don't know how to draw the kind of the triple going around. Okay, maybe that's not the best drawing of K43 I ever did in my life. And but I hope the graph is, I don't think it's actually an illustrative drawing. So let me erase it. So if you look at this construction, we immediately spot that the density of the edges, where the density of this hypergraph comes from, is not uniformly spread. But we have some dense part and we have some sparse parts. So in particular, if let's say I look at this set of vertices, I will see no edges. And this motivates the definition of the uniform Turán density. So the uniform Turán density will not be looking at the density or the maximum density or the maximum number of edges. So maximum density or the maximum number of edges I can have, but it will be looking at the maximum number of edges or the maximum density I can have subject to the uniformity condition, meaning that I do not have a part of my hypergraph that is sparse, that is edgeless, or that may be close to edgeless. So let me now go with the definition. And I should say that that this type of questions they were asked first by Erdős and Sós in the 80s. So let me now give a formal definition. So the uniform Turán density of H is the infimum over all D, such that there exists positive epsilon and 0, such that every, and now let me write here hypergraph, even if the notion makes, of course, perfect sense for graphs as well. Every n-vertex hypergraph satisfying, so what I need here is that n is at least n0, satisfying that every subset of epsilon times n vertices has density D, contains H. So what I wish that if I have my host graph, whenever I look at a subset of vertices which is linear in the size, so there's some epsilon, when I need to see on this subset of vertices density at least D, and if this condition is satisfied, and if that implies the presence of the graph, then that's the uniform Turán density of H. So clearly, if D is 1, then this would be satisfied because I'm just saying that all the edges must be present. And the question is, what is the smallest value of D that this is satisfied? One can also go in the complementary way, which one can also be asking, and of course it's the same problem, what is the largest, and let me call this epsilon density. What is the largest epsilon density of H-free hypergraph for epsilon going to 0? So basically the same question we have seen in the Turán setting, except now asked in the hypergraph setting. So the definition is technical. I hope that it was clear enough how I presented it, but essentially the idea is that the constraint we're putting is that if we look at any linear size subset of vertices, what we're going to see a hypergraph with at least the density D. And this would, of course, forbid the construction of the K4-free hypergraph that I have presented in relation to the tetrahedron problem. So now the question is what we can say about this. So maybe let me first. So maybe I will write here some informal definition now that we remember it. Definition will be every linear part density at least D implies where exists H. So that's what informally the definition says. And the situation is quite boring in the case of graphs. And it's not a very simple, but also not very difficult exercise using the graph regularity, but the uniform Turán density of any graph is 0. So whenever you give me a large graph and you guarantee me that every linear size subset has a positive density, where the linear is quantified by the density you're going to guarantee me, then I can find the given graph in this large graph. But the situation is much more interesting in the case of hypergraphs. So for example, let us go back to the tetrahedron, which actually was one of the hypergraphs that Erdős and Shaw specifically asked, and they actually first asked if it's actually what's known at that time for graphs, it actually extends to the hypergraphs, whether it's actually the case that the uniform Turán density of every hypergraph is 0, but it quickly turned out that this is not the case. And actually, the uniform Turán density of the four vertex free uniform complete hypergraph is still an open problem, but the conjecture is that this density should be 1/2, and let me show you the construction. So what we're going to do is we're going to take the vertices. So I need to construct a large free uniform hypergraph such that all non-trivial linear, let's say, size subsets of its vertices have density at least 1/2, but this hypergraph still fails to contain K4 free. So what I'm going to do, I take the vertices, and now I will be coloring, and I would be almost willing to say edges, but it's pairs, because like I'm going to construct a free uniform hypergraph, so I want to refer to the edges of that hypergraph as edges. So let me say I will be coloring pairs of vertices with 2 colors. So I randomly color pairs of vertices with 2 colors, let's say red and blue. And the condition will be that a triple will form an edge if the colors, so I numbered these vertices, let's say from 1 to n, if the colors incident with the smallest of the free vertices do differ. So basically, I will ignore the color of the between the middle and the last vertex. This is a different blue. And if the colors of the two pairs containing the smallest vertex are different, I will put this as a triple. So it's very easy to see that each triple of vertices is an edge with probability 1/2, because I need these two pairs to be colored differently, which happens with probability 1/2. And it's a simple exercise. Maybe one would need like to use Azuma's inequality, but it's not difficult. But actually, if you give me a linear size subset of vertices, when the expected number of edges I see there is 1/2, and there's a concentration, and so with exponential decay, exponential in cubically in the number of vertices, the number of subsets is exponential. So it is just a single exponential. So it's easy to see that I will not see any large deviations, and I get a hypergraph where any linear size subsets of vertices have density 1/2. And this hypergraph does not contain K for free. So why is that the case? So if it contains K for free, so when I look at the smallest of the four vertices forming it, I look at the edge incident with the smallest vertex, let's say between the first and the second, let's say it's blue, when the colors of the other two pairs will be red. But that means that the first, third, and fourth vertex cannot form an edge, because the two pairs involving them and the first vertex have the same color. So clearly this construction avoids K for free, and the uniform density is at least 1/2. So it shows that the uniform Turán density of K for free is at least 1/2. And the conjecture is, which is open for, I believe now, more than 30 years, but this is actually the best possible construction. So before I go to the results that I want to be presenting today, I kind of want to show actually, I think this might be now a good time to give actually I think a very interesting open problem. But to motivate that problem, I would like to mention another question of Erdős and Sors that they ask and show actually the extremal construction. So maybe this might be actually a good time to check if there are any questions. I don't see any in the chat. I also don't see. Question is, are there some upper bounds? And the answer is yes, they are, but I don't know any interesting from the top of my head. Yeah, so I mean, certainly, like it will not be hard to show it's below 1. It will actually, I can imagine like quickly showing some reasonable separation, but I wouldn't like to claim any partial scalar number, and I don't think that any bound actually. Thank you, Bernard. So the flex says 5 to 9. Thank you, Bernard. But I believe that without flex, one can also go like quite away from 1, but and I don't know like how far. So let me now go to mention another quite simple free uniform hypergraph, and this one will be K for free minus an edge. So it's again a hypergraph that Erdős and Sors specifically ask about. So it's a hypergraph which is obtained from K for free after removing an edge. So we take this triple, and this triple. And where for a long time it was it was a conjecture that the uniform Turán density should be quarter, and now it's actually a theorem. And we have actually 2 independent proofs. One was obtained by Roban Glebov, myself, and Honza Volec. And the other one was obtained by Reihe, Rädel, and Schacht. And I even noted here our paper appear in Israel Journal of Mathematics, and the other paper appear in Journal of European Math Society. So our proof uses Fleck algebras actually, which Bernard mentioned in the remark. The proof by Christian, Vojta, and Matthias is computer free, and it actually started a kind of an area of like using more hypergraph regularity, but I actually will talk a little bit more in a second. So let me show the extremal construction, and then actually I will use it to motivate one problem that it's not unfortunately mine, but even if it's a natural problem, it's a problem due to Reihe, Rädel, and Schacht. And I do find that problem actually very natural. I personally believe it's true, and I think it would shed a lot of light in this area. So let me first show you the construction of the uniform Turán density for K4 free minus is at least quarter. So again, I need to present the construction, and the construction is very similar, or somewhat similar. So again, we take vertices, and now I will be ordering the pairs. So I will take a pair of vertices, and I will order it either from left to right or right to left randomly. So I will flip a coin, and depending on the outcome of the coin, I assign an orientation of the pair. So I will just denote this by drawing an arc. And now I will put an edge if the pair is cyclically oriented, so meaning going either this way or going, sorry, if the triple is cyclically oriented, so that means going this way or this way. And again, it's easy to see that if I'm choosing the orientation of the pairs randomly, the probability that the triple is cyclically oriented is quarter. And again, using concentration bounds with high probability, actually probability going to 1, the epsilon linear density of the constructed hypergraph will be 1/4, or maybe it's just slightly below 1/4. And why does this hypergraph does not contain K4 minus an edge? So actually the orientation was somewhat immaterial. So I may kind of assume that I have 4 vertices. And if I see an edge on this triple, then that forces me how these pairs are oriented. But when I immediately see that the remaining 2 triples cannot be cyclically oriented, because I have a problem here and I have a problem here for the other triples. So I cannot create a K4 free minus in this way. So so even at the first sight, this construction may look slightly different from the one I showed for K4 free. When it's actually the same type of construction, because what we may do is, instead of orienting edges, we may decide to color them. And if an edge goes from left to right, I color it red. And if the edge goes from right to left, edge, I mean pair, apologies, I color it blue. And now the condition for including a triple would be that I take the order and the top edge differs from the 2 bottom edges. So actually I do see the same kind of type of construction, meaning I have some vertices, I ordered them, assigned to their pairs colors. And once I have done this, I decide what triples of colors actually will correspond to the edges. And And this leads clearly to a more general way of proving lower bounds for on the uniform Turán density. So let me just formalize the notion that I have just introduced. So lower bound uniform Turán density. So what we made, so just a straightforward generalization of what we have seen so far. I take vertices. Now I will have k colors. So I randomly assign each pair of them a color. And when I will have some subset, let's call it A, of triples, and if I have a color I, J, and maybe this K was not the most fortunate, so let me write here M, IK, when this will be, this is an edge, this, an edge, if and only if the triple IJK belongs to A. So I kind of decide what will be the triples of colors I wish to include among these. So I'm coloring pairs with M colors. Then I look at all M cubed possible ways how to color the triple, and I decide which of them will form an edge. So I can call this a coloring scheme. It's easy to see that if I have a coloring scheme and a large graph, when the uniform density of the produced hypergraph will be the size of A divided by M cubed. And again, like the martingale arguments, concentrations will go through. And in my notes, I have, it's a conjecture. So I hope that I'm not promoting a problem to a conjecture due to Ryer, Redl, and Schacht. That the uniform Turán density of H is equal to the infimum over the density of all coloring schemes avoiding H. So the density of the coloring scheme, not surprisingly, will be just this number. So this number I will refer to as the density of the coloring scheme, because as the uniform density of the hypergraph that is going to be produced. And by avoiding H, I just mean that H cannot be a subgraph of the graph obtained using this coloring recipe. And this we have seen that this is actually true for K4 3 minus, because where the best coloring scheme can do quarter and we can prove quarter. And it's conjectured to be the case for K4 3, and actually it's the case for all, and well, not so many actually, for all free uniform hypergraphs for that we do know the uniform Turán density. So essentially, the conjecture, if true, says that instead of looking at hypergraphs, at all hypergraphs, when one would be studying the uniform Turán density, when it would be enough to look at the coloring schemes, which in principle should be a much simpler task. So now I might be like slightly after the half of my talk, but now I will start coming to the results that I wish to present. But maybe I should again like ask if there are any questions or comments. So the question is how easy. So I'm repeating the question just for the mic because I'm not sure whether the mic got the question. So the question is how easy is it to check whether a particle coloring scheme avoids a graph H, and it's super easy. And the reason is it doesn't avoid. So maybe I should do an example. So let me. So I think we do understand what is it. So basically, in order to show it doesn't avoid, it's enough to present the ordering of the vertices and the coloring of the edges. So for example, if I look at the first coloring scheme, that was the one for K for 3. So that should contain K for 3 minus an edge. And indeed, what I need to do is, so I'm looking at the one with the density half. So let's say I color this pair blue, this pair red, that already included me 2 edges. And maybe what I need to do is I just need to color these 2 pairs with these colors. And I immediately see that however I color the remaining 2 pairs, I have K for 3 minus an edge. So essentially what I need to check whether a particle coloring scheme contains a hypergraph, I just need to present its ordering of the vertices and the coloring of the pairs of its vertices, which is a simple task. The trouble is that I don't bound the number of colors in the coloring schemes, or at least it's not a priori clear that I can do that. And basically, there are a couple of open problems here. But first of all, it's not clear whether this infimum is actually minimum. And the second is whether there would be some reasonable bound on the number of colors one needs to use in coloring schemes for hypergraphs, let's say with 10 vertices, 11 vertices, just a bound depending on the number of vertices. So if this conjecture is true, then we should have actually an easy classification of graphs with uniform Turán density. So basically with 0 uniform Turán density, because basically the conjecture would be saying that if there's a non-trivial coloring scheme avoiding H, when the uniform Turán density of H cannot be 0. And that's actually now a theorem. And that's a theorem which motivated one of our results. So it's a theorem due to Ryle, Redl, and Schacht. Somewhat more recent, 2018, Journal of London Math Society. And they showed that the uniform Turán density of a hypergraph H is equal to 0 maybe let me change the color. If and only if, and let me now call it a vanishing coloring, and I'll explain in a second what it is. H has a H has a vanishing coloring. And a vanishing coloring of a hypergraph H is a coloring where I order its vertices and I color their pairs with 3 colors, let's say red, blue, and green, in such a way that all edges are of this type. So all edges will be colored red, blue, and green. So all edges of H look like this. So the theorem classifies which hypergraphs, free uniform hypergraphs, have 0 Turán density, and the classification says that it's if and only if it's possible to order the vertices of H in a way that and color their pairs in a way with 3 colors, red, blue, and green, in a way that every edge of H looks like this. And of course, this is equivalent that there is no non-empty coloring scheme avoiding H. Yeah, because if I have any coloring scheme that contains at least one triple, when I will just think of a triple as red, blue, and green, and I will discover my hypergraph H in sufficiently large hypergraph obtained according to this coloring scheme with probability 1. So there's another corollary of this. So if the uniform Turán density of H is not 0, then the coloring scheme containing 3 colors red, blue, and green, and only the triple red, blue, and green is actually H avoiding. Yeah, so let me write it. So if so corollary, if H does not have 0 uniform Turán density, when the coloring scheme with H, with 3 colors which contains only a triple red, blue, and green avoids H, which implies that the uniform Turán density of H must be at least 1/27, because I have just shown you a specific lower bound construction, and its density is 1/27. And Ryer-Redl and Schach specifically asked if actually this is tight, because in principle I did not have any example, and that's actually our first result. So this is a joint work with 2 postdocs of mine, Frédéric Garbe and Ander Lamaison. And we showed that such hypergraphs do exist. So we constructed not only one, but the whole family of 3 uniform hypergraphs with density 1/27. So we actually have a sufficient condition. We don't have a necessary condition. So maybe let me write down our condition, and when I maybe say a little bit about the proof of the theorem of Ryer-Redl and Schach, and also of how we extended it to get our result. So just to check the time, I do believe I might go for another 15 minutes. Is that fine? I started a little bit late, but I don't want to. Okay, thanks. So maybe let me first state our result. And so what we proved is that the uniform Turán density of H is equal 1/27 if. So first of all, H has no vanishing coloring. And the reason is if it has a vanishing coloring at 0. So maybe let me also draw here, because it will be important. What is how the triple looks? This is the triple of colors appearing in the vanishing coloring, and it will be important for the next 2 points. H can be H decomposed into H1 and H2. H1 and H2 have vanishing colorings. With the same order of the vertices. So I can order the vertices, and when color pairs, possibly like separately for H1 and H2, so I first order the vertices of H. When I decompose or split the edges of H into two hypergraphs, H1 and H2, and I have prepared an example, so I explain it in a second, but first let me state it, into H1 and H2 in such a way that both H1 and H2 do have vanishing colorings, and the overlap is among the green edges in H1 and the red pairs in H2. So I have kind of the split, the edges of H1 and H2, if they do contain two vertices, their intersection, but it must be the case that and maybe I should do here an example or a better picture. Then it must be the case that the edge of H1 kind of is the top edge, or is the green edge in H1, but so this would be an edge in H1, and the same pair appears as the red pair in H2. So the two vanishing coloring do not need to be different, but I'm heavily restricting the way they do intersect. And the intersection can only be that if a pair is green with respect to H1, it's red, then it can be red with respect to H2. And I'm forbidding all the other combination of pairs. And when there's a third condition, I also need to have a pair of vanishing colorings where the overlap is red and blue. So let me move at H1. And if a particular hypergraph H satisfies these three conditions, when its uniform Turán density is exactly 1/27, we have the whole family. But I also prepared one small example that I wish to show now. So let's see whether the technology will work. And the technology worked. So this is an example. So the hypergraph is the one in the left. The split between H1 and H2, that does not need to be the same for the second and the third point, but it actually happens to be the same here, is that the triples that are denoted by solid triangles are the triples and one of the hypergraphs, and the other hypergraph just contains a single edge, namely this edge ABG. And the two colorings on the left and right, together with the ordering of the vertices, they show the existence of the vanishing coloring of all edges of the hypergraph containing all edges except the dashed edge. So for example, if I look at this 1, 2, 7, I see that the edge 1, 2, or the pair 1, 2 is red, the pair 2, 7 is blue, and the pair 1, 7 is green. And now if I look at the overlap here, so I have here the pair 2, 5, 6. So the only overlap is on 5, 6. In this vanishing coloring, in the vanishing coloring of the big part, it's red, and 2, 5, 6 would mean it's blue. So this shows me that the condition 3 is satisfied. So this shows me that the condition 3 is satisfied, and this coloring hopefully will show that the condition 2 is satisfied. So I have an overlap on 2 and 6. So 2 and 6 in one is red, and I say it's 2, 3, 6, so it would be green in the other. So it shows that 2 is satisfied. And we were able to construct an infinite family, but I don't want to present it. Instead, what I wish to say a little bit about the proofs, and in particular because it will kind of reappear in the second result. I don't want to go into too much details with the proof, but I want to very briefly sketch how the classification of the uniform of the hypergraphs with zero uniform Turán density was done, and then just give a hint what we did to actually obtain our result. So I think I actually may go to the so now I'm giving a sketch of the proof of the theorem of Ryer-Redl and Schach, that the existence of vanishing coloring implies zero uniform Turán density. And the proof goes through the hypergraph regularity. So I do assume that many of you are familiar with the graph regularity, which allows splitting vertices of a graph into subsets such that the edges are quasi-randomly distributed between them. The hypergraph regularity is a little bit more complex in the sense that we split the vertices into subsets. But now, in addition to vertices, we also need to split the pairs of vertices between different parts. So we need between each part, or between each pair of parts of vertices. So the potatoes I drawn are parts of vertices. The pairs, I split all their pairs into several subsets. I can think of those as complete as a splitting of the edges of the complete bipartite graph in such a way that these pairs are quasi-random. So I will have maybe another split here, another split here, another split here, and so on. And now in the what the hypergraph regularity restricts is that when I take 3 of these parts and I look at specific pairs, so let's say I take blue pair, another blue pair, another blue pair here, then if I'm looking at the edges formed by these vertices which are in these colored pairs, when these triples are quasi-randomly distributed. And we're quasi-randomly distributing among all triples. When I take a vertex here, vertex here, vertex here, this pair is red, this pair is blue, and this pair is blue. So in the graph regularity, I would just have a condition on taking a vertex from one set and another. Here, it's not enough to take a vertex from one, second, and third set, but I also need to go through this restriction of the pairs. And what Ryer-Redl and Schach did is that they look at the hypergraph regularity, that actually like Vojta and Matthias were like at the developing of, and they shown that for each, if I have a hypergraph with a positive uniform Turán density, then it's possible to choose these colors, and I will now denote them alpha, beta, gamma, in a way that the triples alpha, beta, gamma will always have a positive density. So in other words, what they've shown, if the hypergraph is large enough, it's possible to take a vertex from each of these parts, when for each of these parts kind of choose and maybe, okay, the vertex might depend on the color, but there will be a choice of alpha, beta, and gamma in such a way that whenever I am taking 3 pairs in this order, and I take alpha here, beta here, and gamma here, this will be kind of a dense triad. And what we did, and I mean, I don't want maybe to go into further details. What we did is we kind of inspected what happens when we reach this threshold 1/27, and when necessarily some of these choices might overlap, and that leads to the condition in our theorem. And somehow a similar argument is also behind the proof of the second result that I want to mention. And I think I might have still 5 minutes, but maybe not more. Maybe more. However, I want. Okay, 1 hour. Okay, not so much. Okay, so I state the result, and I kind of explain it, and then I will conclude. So I will conclude latest in 10 minutes, but I will try to do it within 5 minutes. So the second result is that we look at a specific family of 3 uniform hypergraphs, which is the family of so-called tight cycles, which is also a family which was mentioned in actually a very nice and very accessible survey of Christian Reyer on uniform Turán density and its variants. So a tight cycle is what one would expect. One takes cyclically ordered vertices and takes all, and I suspect I'm not doing maybe I'm doing a good job. Take all pairs of vertices, all triples of vertices that are consecutive. And then we can ask, what is the uniform Turán density? What is the uniform Turán density of CN3? So we knew that for C5-3, we suspected the answer to be 4/27, because there was a proof which was actually coming from the master thesis of J. Cooper at Warwick, but that's the best you can do with the coloring schemes. And what we actually did is we actually showed that this is indeed the best. So what we can do is that it's equal to slightly different color. But it's equal to 4/27 if n is at least 5 and not divisible by 3. It's 0 if n is divisible by 3, and this just follows from the classification result of Reyer, Redl, and Schacht. And I kind of skipped here n over 4, and that we don't know because there's the complete 3 uniform hypergraph. Like you may verify that's the one. So here there's a conjecture. So of course our original aim was to particularly settle C5-3, but we managed to actually settle the case of all tight cycles. And when we started this project, we thought that in particular, given that there was like a lower bound proof, we knew the situation with the coloring scheme, that it will not be so difficult because we just take the proof from the coloring scheme and somehow translate it to the regularity. But it actually turned out that our optimism was not quite in the place. However, what we managed to do, we managed to show a general embedding lemma, which I just show you, but I will not go through it, which says that if I have and I call it partition hypergraph, but with actually the regularity partition with density larger than 4/27, when we have 4 specific configurations, but at least one of them must always appear. So these are, and again, the proof is, as you would perhaps expect, we inspect the hypergraph regularity. And in each of these situations, and let's maybe directly here, in each of these 4 situations, we actually managed to embed the tight cycles. So here is an embedding of 5 cycles in the 4 possible outcomes. So how one should read it The dots do represent the parts in the hypergraph regularity. The Greek letters do represent the choice of these quasi-random bipartite graphs. And when, for example, in the first case, if I go back here, maybe I make some notes. In the first case, we guaranteed that we always will be able to complete an edge with colors alpha, beta, gamma, with alpha, omega, and gamma star, and omega and gamma. So this one should read that one is when we have this partition in the regularity, when there will be this color of pairs here alpha, the colors of pairs is beta, and colors of pairs of gamma, such that this will be a dense triad. And we can see that actually this exactly corresponds to this picture, because we have alpha, gamma, and we complete here with beta, which is the good beta with respect to this alpha, omega with this alpha and gamma star. And we have here gamma star and omega, which we can complete with a good alpha here, and so on. So as I said, the proofs go like through, I mean, we didn't go directly to the hypergraph regularity. What we did is we actually like inspected structures which are equivalent to hypergraph regularity, that give us some conditions on which pairs of vertices can form edges in the triads in the regularity, that led to this lovely optimization program that I was slightly optimistic I can say a few words about, but I don't think that I have time for that. And we solved this optimization problem. So even if this optimization problem, when you look at it, doesn't look terrible, it looks like something that one should do straightforwardly. It actually took us a week. Like we had a numerical solution, but to actually show that 4/27 is the minimum was not so easy. And I think I did a better job when I was presenting the result of the cycles. I should have said that it's a joint work with Matija Bučić, who was a PhD student at ETH and is now a postdoc at Princeton, with Jay Cooper and maybe so. So let me maybe rewrite the theorem. And so the theorem with Matija Bučić. At the time when we were working, he was at ETH. Jay Cooper, who's my PhD student, and he's the same student who did the coloring scheme, upper bound earlier. Samuel Moore, who's my postdoc, and David Munha Korea, who's a PhD student at Zurich. So our theorem says that the uniform Turán density of CK3, K at least 5, K not equal 0, is 4/27. And so let me just finish with a couple of open problems. So I already mentioned the conjecture concerning coloring schemes, which I personally find like a beautiful conjecture, and I would really wish to see its solution. I personally believe it's true, but maybe when it's not a problem for me, as Bartek pointed out, I'm good at disproving, not proving. When the second problem, and what we don't know is, so we saw that there is no hypergraph with uniform Turán density between 0 and 1/27, and we don't know if there are hypergraphs with uniform Turán density, let's say arbitrary close over 4/27. So is it true that for every epsilon where exists D between 4/27 and 4/27 plus epsilon, and this should be exclusive, such that there exists a hypergraph with uniform Turán density. Equal to D. And of course, one can ask this question more generally. So we also don't know the answer if we write here 1/27. And we actually don't know the answer if there are even some numbers which would not be gaps. We know that there will be infinitely many uniform Turán densities, in particular if one looks at the set of complete free uniform hypergraphs, and this set would provide us an example. But we just don't know, like, if all of them, let's say if this is false, let's call that number a jump, because there's a jump where simply no uniform Turán density is larger. We don't know if all uniform Turán densities are jumps or there are some non-jumps. And with this, let me thank you for your attention.